All right, what is up, everyone? Welcome back to the YouTube channel. I'm Xavier Smith, and today I'm going to go over AP Statistics Unit 6, Part 1, which has to do with Z intervals for one sample Z intervals for population proportion, and one sample Z tests for a population proportion. Okay, so I just threw up a few whiteboards, and instead of going through everything in detail and giving you a 2 hour long video, which I could do, I'm just going to go over examples for each thing and try to explain it as I go. And then once you watch it once, maybe it'll click, or maybe you watch it again. And again, I'm going to do my best to explain everything, but then again, I don't have that much time and I've got tests this week, so I'm trying to do the best I can. All right, well, enjoy because it's gonna be a doozy. All right, so starting with a confidence interval. All right, I'll just read the question and then go through it and try to explain as I go. Okay, a recent poll of 740 randomly selected cell phone users found that 170 of the respondents admitted to walking into someone or something while talking on their phone. So construct and interpret a 95% confidence interval and confidence level. 1 second, let me grab my calculator real quick. Okay, I have my calculator now. Should have grabbed that beforehand. All right, so the first thing we want to do is state what we are actually doing. There's 4 steps here. So we are going to state what we are doing. So we are making a 95% confidence interval. I'm just going to say 95% confidence interval. And I'm going to say, like, this is a one sample, because we only have one sample, Z interval, because we're using normal distributions here, which has to do with the Z test. So you say Z interval, like Z score. So like one sample, Z int for P, right? Where we say P equals, and then we give context. So P equals proportion of, I don't know, cell phone users like those in the study, like those in the study that would admit into walking, would admit would admit to walking into something or someone while on their phone. And then this is really the most context you have to give. Later on, like in another video, when we do 2 sample Z intervals, you have to give a lot more context. But this is really good context right here because it tells exactly what you're doing for the rest of the problem. And again, you could always say like the p hat, like our statistic here would be 170 out of 740, but we're going to do that later. Okay, now that we've stated what we're going to do, we have to check appropriate conditions. We have to check if this is independent, if it's random, so it can be applied, like the results can be applied to everybody in the study, and independent is that the results can actually be applied to the total population. And then finally, if it can be like a normal distribution can be used for this data. Okay, so we had state. Now we say check. All right, so first of all, we have to check if it's random, if it can be applied to like everyone that's in the study. Okay, so random, right? And here it's just going to have to say in the problem it's random, and it said it's randomly selected. So I'm going to say that's a simple random sample. Check. Okay, now we need it to be independent. And independent means that it can be like attributed to the whole population. Here would be the whole population of cell phone users, right? So the way to find independence, because like without replacement, is that it has to be less than 10% of the total population. Well, so that's just like 10% right here would be like our independent. And we're going to say 740 is less than 0.1, which is 10%, all cell phone users. And yeah, it's safe to assume that there's at least 7,400 cell phone users. Duh, right? This video could get 7,400 views. It's not going to, but it could, right? So we're going to assume that there's at least 7,400 cell phone users. And a lot of times you just assume 10%. You could always just say, like, instead of this, you could always say safe to assume that 740 is less than 0.1 all cell phone users. Okay. And then finally, it has to be used with a normal distribution. And the way to make sure it can be used like with a normal distribution is large counts. It just has to be, there has to be enough successes and failures that it can be shown by a normal distribution. And we learned about that in another unit, an earlier unit. So I'm going to put LC for large counts, which means NP is greater than or equal to 10. This is really N hat. And like P hat, because this is our statistic, we don't have anything else. We don't have a P. We don't have what the actual proportion of people that walk like would admit into walking something while on the phone. We only have like a statistic, so we have to use a statistic here. And then N times 1 minus P hat is greater than or equal to 10. So the number of successes and the number of failures has to be greater than or equal to 10. Well, successes would be proportion of people that walked in the phone. 170 admitted. So 170 is greater than or equal to 10. Good. And then 740 minus 170 would be the people that didn't admit to it, would be 570. And 570 is also greater than or equal to 10. Okay, so our conditions are met. Now what do we do? Well, we have to calculate. Now we know we can calculate. So what do we do? All right, first we need our statistic, which our statistic is 170 out of 740. And we say P hat is statistic here, equals 170 out of 740, which equals, turn that into a decimal, equals 0.22. We're going to say 0.23 to make it easy on us. Okay, now that we have that, a confidence interval is basically our point, like the general formula for it is point estimate, PE, plus or minus margin of error. So we have our point estimate, and then it's plus how far, like margin of error is the maximum distance we think that the true proportion, like true proportion here in context, is from our point estimate. So we just do point estimate plus or minus that margin of error, and we think that it's going to be in that zone. And clearly, if we're more confident, like 95% confident, we're pretty confident that it's going to be in that zone, then we're actually going to have to use, like, the more confident you are, of course, the wider range of values you have to be able to accept, because you're more confident, so you have to go over a wider range of ideas. Well, like numbers. Okay, so point estimate plus or minus margin of error, which is also written as P hat, which is our statistic, plus or minus what they call Z star, which is our critical value, which has to do with how confident we are, 95% confident, times, they don't use standard deviation anymore. They use standard error, which is like the same thing. It's the root of P hat times 1 minus P hat over N. Instead of standard deviation where they use P, we just use P hat, right? It's not that hard. And then we just plug in. All right, 0.23 plus or minus. And what this Z star here means is if you had a normal distribution, which we're going to have for this, Z star, this 95% just means we are looking at the middle 95% of data points, right? Because then any other data point that like won't fit in our conclusion will be out here and it won't happen very often. So we're looking at the middle 95% of data points. And for that, you are going to go into your calculator. Okay, so you'll go into your calculator. You'll go second theirs, and then down to inverse norm. If you have one of these new calculators, area 0.95, our confidence level, and it will be in the center. All right, and then you paste, and you get 1.96, negative 1.96. You just need 1.96. Okay, plus or minus 1.96. The root of the P hat, 23 plus, well, 0.23 times 0.77, 1 minus 0.23, 0.77, yeah, over our N was 740 people. And then again, you can plug this, you can plug all this into your calculator and get an answer. But then again, there is also an easier way to do this. Let me just find it. 1 proportion z interval. Okay, so here it is. You could plug that into your calculator and get the correct answer, or you could go to stat, over to tests, and then down to 1 proportion z interval, which is what we said at the top when we stated. You click that, and then you put in your x, which is like your 170, right? And then you put in your n, which is your 740 people, and your confidence level is 0.95. And then calculate, and you're going to get your p-hat, which is correct, 0.229, which is 0.23, your n, and it will give you this confidence interval, which is the same thing if you just plugged this in and got your margin of error, and you added and subtracted from the point estimate or statistic, you would have got the same answer. So we're going to get 0.199, comma 0.260. All right, so what we have from this, when we interpret, I might not write this out because I don't have much room, but you're going to have to remember this. So our 95% confidence interval is basically, you just say, we are 95% confident that the interval from 0.199 to 0.260 captures the true proportion. Again, just like restate this P, captures the true proportion of cell phone users, like those in the study, that would admit to walking into something or someone while on their phone. All right, that's it. You're just like, we're 95% confident that this interval captures P, but give P in context. And then a confidence level is even simpler. You don't need all this data. You don't need this interval or anything. You just say, okay, like, given that we have, like, assuming, like, if we take, okay, this is it. If we take many samples of the same size, so of size 740 from the population, like, of cell phone users, and create a 95% confidence interval with each of these samples, about 95% of them will capture the true proportion of cell phone users like those in the study that would admit to walking into something or someone while on their phone. So again, you're like, if we were to take many of these samples, just like the one we have, right, of the same size and the same confidence interval, and we made a confidence interval with each of them, then about 95, like this confidence interval level of them would capture the true proportion of P. And this is because if you were to make a lot of these 95% confidence intervals, 95% of the time, they're going to capture the true proportion. That's why you're 95% confident about it, because it captures the 95% middle points. These are outliers over here. Only 5% of them end up over here. So if you were to create many of these 95% confidence intervals, 95% of them would capture like all the, like the true proportion, because the true proportion is probably somewhere in this 95%. Okay, I hope that makes sense. You can always comment if it doesn't. But we got to keep moving because we got a lot more to do. All right, this is a simple one here. I just had to throw it in case it's a question on your test. My gosh, I can't set this down. So if it's any question saying like how big of a sample is needed, it'll give you some like, it'll just yap for a bit about the problem. But basically, it'll say like a 95% confidence interval or something. It can always say like 99% confidence interval, 90%. You just do the same thing on your calculator and get the critical value. 95% confidence interval with estimate within 3 percentage points. And what that estimate within 3 percentage point means is that your margin of error is 3 percentage points, 0.03, because it's your point estimate, and then within 3 points to either side would be plus 3 points or minus 3 points. So if we just plugged in values, this z star here, again, it would be just like we had in the other equation, z star of 95%. Put in your calculator, you'll get 1.96. Root of, since we're not given a p-value here, we're not given a proportion of whatever this is, whatever the context is, we're not given a proportion, so you always assume that the proportion is 0.5. And you could write that on the side. Assume p equals 0.5. Because you're not given anything and p equals 0.5, is just a safe answer. So you say 0.5 times 0.5 over n, which we're solving for. And then again, we said within 3 percentage points. So it's either less than or equal to 3 percentage points. So less than or equal to 0.03, right? It can't be more than 3 percentage points away. So we say the margin of error has to be less than or equal to 0.03. Because if you remember when we said for a confidence interval, the general formula is point estimate plus or minus margin of error. And we said margin error is the same thing as the z star times standard error, which is critical value times standard error. So now we just plugged it into the formula. All right, now we solve, and we'll do 0.03 divided by 1.96, and then we're going to square that, and we'll have, that was not squared, 1 second, squared, and now we're going to have 0.5 times 0.5 over n is less than or equal to 0.01, 2, 3, 4, something times 10 to the negative fourth. 1, 2, 3, 0, 2, 3, 4, right? It's something like that. You didn't even have to write that down. And then you can multiply the n over here and divide this 0.25 by this value. So I'll just do 0.25 divided by that value. And you get n equals 1067.1, but you're always just going to round up on these numbers to be safe. So n equals 1068. If you round it down, I don't think you're wrong, but you're not going to have like 0.1, like a tenth of a person. So just round up and say like 1068 people. All right, well that was one. Now we are on to the second part, the z-test, which should go faster because, I mean, we have to learn a little bit more hypothesis testing, but it's the same little like state, do, calculate, conclude. And we're not talking about confidence levels. Let me see which one I need. Okay, I need this side. All right, 1 second. All right, so we're just going straight into this. The one sample z-test for P. So you cannot have more than 8% of a shipment with blemishes. This is about potatoes. And you take a simple random sample of 500 potatoes from a truck, and 47 have blemishes. Is there convincing evidence more than 8% of the shipment is blemished at alpha, which is your significance level, equals 0.1? Usually we used to say, like, is this statistically significant? And it's like, are the chances of this happening less than 0.05? And if they're less than 0.05, it's significant. It happens less than 5% of the time. And here we're saying, is this outcome here, 47 out of 500, is this statistically significant? Where statistically significant isn't like 5% anymore, it's 10%, right? We're being a little more conservative. Okay, so this is what we have to do. Again, we have to state. Number one. Okay, so first to state, now we do in the one sample z-test, which we're going to say one sample, because it's only one sample, z-test for P. It's not asking about an interval, and it's asking if it's significant, so it's a z-test. You're just finding the z-score of it, the probability of it happening, and then comparing it to the statistically significant here. Okay, so now what we have is we have a hypothesis here. And what we're going to say is there's a null hypothesis, which we are given. Like, we're given and we're supposed to not accept it, but imagine it's true and then compare our other hypothesis against it. Might not make sense at the start. And then HA is going to be our alternative hypothesis. So HO is that P equals 0.08, right? The proportion of like potatoes that can have blemishes is 0.08. So we're going to say, okay, maybe the proportion is 0.08, right? And then here we're saying, is there convincing evidence that more than 8% of the shipment is blemished? So we're saying, okay, is there convincing evidence that P is actually greater than 0.08? So greater than 0.08, right? And this is saying that like, like HA is that the P is actually greater than expected in HO. Whatever. You're just saying, okay, it's given that 8% can be blemished, which is HO. You just say like, okay, we kind of accept that only 8% can be blemished. All right. And then the other person saying like, hey, but is there more than 8% here? Is more than 8% blemished? And that's what we're trying to find out. Okay, so now that we have that, you say P, like you have to define P. You also have to give significance level, but you just throw that there. Significance level, which is alpha. That's not 0.01. That's just 0.1. This is just significance level. It's also called alpha. It's a weird little symbol. And then you say P equals proportion of blemished potatoes. I don't know. It's not that much. I'm not giving that much context. But again, I got to get to bed. So P equals proportion of blemished potatoes. Now we've stated everything we need to, right? Now we are going to check, and we check the same things. Before random, right? It's an SRS. It's a simple random sample. Okay, 10%. Again, 47 is less than 500. So, well, 47 is less than 10% of 500, right? Because 47, our sample size, is less than 10% of the total population. So therefore, it is independent. The conclusions based on these 47 potatoes can be given to the rest of the population. So that's 10% correct. And then large counts, and P is greater than or equal to 10. Well, N times 1 minus P hat is greater than or equal to 10. Here, just saying successes. Actual blemished tomatoes is greater than or equal to 10. 47 is greater than or equal to 10. Check. And then whatever the other one is, that's probably 453 or something. 453 is greater than or equal to 10. Like unblemished tomatoes, there's more than 10. Potatoes, sorry. Okay, now that we checked, holy, I hope you guys are getting this. Now that we checked, we're actually going to calculate. Okay, so calculate. Again, this is the same thing as finding a z-score and then seeing if it's statistically significant. So our general formula for a z-score is statistic minus parameter over standard error, which is usually standard deviation. Okay, and then we just say statistic is our what is it? It's our p hat, and we're given a p hat, which is 47 out of 500, minus p, which is the same thing. Like they call it PO to make it simpler, but a lot of people don't get that. It's basically your p, your parameter is given in your null hypothesis. So your null hypothesis is just the parameter, and then the alternate hypothesis is saying, well, is this sample different than the parameter? Is it different than what we expected? Okay, so I'm going to put PO for some reason, and then over standard error, which here we don't use P hat, we actually use PO because we're given it's really P right now. Like this is the population proportion, so we should just use it. And that'll be 0.08 times 0.92 over N, which is 500. Oh, never mind. I shouldn't plug in yet. Just PO times 1 minus PO over N. And then again, we plug in, which would be 47 out of 500 would be 0.094. That's our P hat minus 0.08, which is our PO right here, like HO, the P of HO, over the root of 0.08 times 0.92. That's a 2 over 500 potatoes. And again, you could put this in your calculator, but I'll show you the way I do it. We go over to stat, tests, and then one proportion z test. And then we plug in what our PO is. Our PO is 0.08, right? And then our X is 47 out of 500. And then we are saying that the P is greater than PO because we have this greater than sign here, we're basically saying that the actual proportion of potatoes that are blemished, like our hypothesis is the actual proportion of potatoes that are blemished is greater than the parameter, which is like the PO here. So we're saying it's greater than 0.08. You'll just see by the symbol you have here. Okay, and then you calculate and you're given everything. You're given your z-score and your p, which is your p-value, which we'll get into. And that's all you need. Okay, so let's do this. So z, like this is the formula for z-score. So we're given z equals 1.15, which if you think of a normal distribution, it would be like here's your center, and your center is really like 0.08. And then your z would be 1.15, which would mean you're 1.15 standard deviations away from the mean, like the HO, which would be our parameter. And that point over there would actually be 0.094. And then we're finding the probability of getting 0.094 or more extreme, just as a z-score is. And by our little p that we're given here, you could plug this into normal here. You could plug this into your calculator and get this value using the z-score of 1.15, but we're just given p-value, which is really like the percentage of points that are like greater than or equal to 0.094 equals 0.124. Okay, and then finally, we have that. Now, is it statistically significant? So the question, is there convincing evidence more than 8% of the shipment is blemished at alpha equals 0.1? Okay, so you say because the p-value of 0.124, and then we say, okay, is it less than or greater than or equal to the alpha? It is greater than the alpha, which equals 0.01, comma, we fail to reject that more than 8% of the shipment is blemished, that more than 8% of the shipment is blemished, 8% of the shipment is blemished, oh my gosh, I can't write. And we do not have convincing evidence. Convincing evidence that we fail to reject that more than 8% of the shipment is blemished. You could say that we fail to reject HO, and we do not have convincing evidence that, I'm just going to draw an arrow, that more than 8% of the shipment is blemished. You could say because the p-value of like 0.124 is greater than alpha equals, that should still be a 0.1, we fail to reject HO. Like we fail to reject the null hypothesis. So we fail to reject the parameter, that it's 0.08. And then you say, and we do not have convincing evidence for HA in context. We do not have convincing evidence that more than 8% of the shipment is blemished. All right, I hope you got that. Again, leave any comments. We got one more. Okay. And then it's done for this part of the unit. Again, ask any questions you need in the comments. I can make more videos. I'd be happy to. I got chem to study for. Okay. Now, finally, this is talking about errors that can occur and what they call power. All right. So there's this little box here. These are like your conclusions and then what was actually true. So if you find convincing evidence for HA, like the alternative hypothesis, of course, you are going to reject HO. You're going to reject the null hypothesis. So here, if HO is true and you find convincing evidence for HA, you're going to end up rejecting HO when HO is actually true. Like you're going to reject the null hypothesis when it's actually true. And that's called type 1 error, which is just equal to your significance level. Saying your significance level is 0.1, there is a 0.1 probability that you make a type 1 error and accidentally reject HO when HO is true. You're not supposed to say it's true, but like when you shouldn't have. Okay, and then if you find convincing evidence for HA, meaning you're going to accept HA and reject HO when HA is true, that's called power. It is the probability of like correctly rejecting HO when HA is true. So it's like just correctly accepting HA when HA is true. So you found convincing evidence for HA and you accepted HA. Okay, and then there's a way to interpret that down here. They'll give you like a p-value. They're like, assume that the actual proportion of blemished potatoes is 0.09. Now, what is the probability that we reject HO? Like, they're giving you that HA is true. Now, what's the probability that you actually say it's true, you find convincing evidence for it, and you reject HO? Well, you'd say, like, assuming that P equals 0.09, we will have A, and they will give you this value here. They're like the power of it's 0.17. And you say, okay, assuming that P equals 0.09, we will reject, like, HA, reject HO. We will reject HO. Oh, why was it that color? We will reject HO, like we will reject that the actual amount of potatoes in the shipment is 0.08, like 0.17, like 17% of the time. Okay, that didn't make too much sense, but it's all right. Okay, and then there's two other things. If you don't find convincing evidence for HA, meaning you are going to reject HA when HO is true, that's just the correct conclusion, just correct. And then if HA is true and you don't find convincing evidence for HA, meaning that you're not going to accept HA, but HA is true, that's called a type 2 error. And that is the same thing as 1 minus power. Like if they give you power, they'll just say like the power is 0.17. Find the probability of type 2 error. You just say 1 minus 0.17 equals type 2 error, which would be like 0.83. Like the probability of type 2 error would be like 0.83. And the reason it's just like 1 minus power is their complements, because given that HA is true, 100% of like 100% of your conclusions are either like you find convincing evidence for HA or you don't find convincing evidence for HA. So either you correctly reject HO when HA is true, or you fail to reject HA. Well, you fail to reject HO when HA is true. So one of these, like between power and type 2 error, when HA is true, they happen 100% of the time. So if you have power, you have the chance that power is like 20%, then you know that the other 80% of the time you're going to make a type 2 error and actually fail to reject HA when you fail to reject HO when HA is true. Sorry, it gets way more complicated near the end. So again, ask any questions you need to. It's getting late at night, so I might be a little off my rocker, but I really do hope it helped at least a little bit for review. Okay, well, thank you so much for watching, and I'll see you in the next one.